start our week 10 lecture slides. Let's download them. Finder and Kyber. We know the passwords. Okay, so we start week 10, binary or binarized neural networks. Guys, this is getting much fun because these are very hot topics. I mean, people are today many scientists are working on it, and there's still no standard for it, so which means there's still many things are open to academic research in this field. So that's why it's getting fun. I hope you're going to like it. What are binary neural networks, guys? Well, binarized or binary neural networks are deep neural networks that use only binary values for activations and weights, for both activations and weights. So you start your network, and inside the network, all the weights are binary, as either logical value 0 or logical value 1. This logical value 0 or 1 might represent mathematically other values. We'll come to that. But binary means you have logical 0 and logical 1 in your weights and also in your activations. Everything is binary. So it is like a binary circuit in your logic design. This is very nice because anything that you build up in an FPGA, for example, is like a logic circuit which is interconnected like a network. So BNNs are very suitable for FPGAs. But I'm not saying that they are not suitable for CPUs or GPUs. Actually, they are suitable for FPGAs and GPUs. And actually, in the following slides, we are going to learn that there are actually specific hardware for BNNs, because BNNs are very powerful and they are most likely to be used very widely in the deep learning, embedded deep learning society. So with binary values, BNNs can execute computations using bitwise operations. So instead of multiplication, since your activation, because this input is the activation of the previous layer, and the weights are binary, the input is binary, the weights are binary, so your multiplication operation becomes bitwise operations. And you all know that CPUs or GPUs or FPGAs, they do bitwise operations much fast, guys. So when you're doing it faster, you'll obtain much fast results, which is the main reason we are doing embedded deep learning. So something to be careful here is, in the figure which I have taken from this website, in the figure, I have not put logical zeros or logical ones. Instead, I've put minus ones and plus ones. Binary values, although they are logically 0 or 1s, their logical representation may correspond mathematically to some other values. Still binary values. There are two distinct different values, but they are not 0 or 1. They can be either minus 1 or plus 1. So plus 1 representing logical 1, set high value. Minus 1 representing logical 0, low, clear value. We'll see that because in a couple of slides I'm going to also show you this. In this case, your usual multiplication becomes the XNOR logical operation, which makes sense because we want to multiply these things, these two values, and they become a single gate operation like XNOR. We could create an XNOR net. Actually, XNOR net is a very famous BNN paper, which we are going to cover in the following slides. Okay, so we've got the idea. Let's try to get more into why of BNNs, why we are using BNNs. BNNs are extremely compact and still yet powerful, guys. Yes, they are compact because you're representing everything either in minus ones or zeros and logical zeros and ones, mathematically minus ones and plus ones. So they must be compact. So you don't have any precision here. It is the lowest precision you can get. Still, they are very powerful. Still, the results of the BNN studies shows that they have accuracy levels almost similar and almost same as full precision, single precision networks. They are not easy to get there. I mean, they are hard to train, but when you can train them, you get them. So generally, deep neural networks require powerful GPUs. I mean, it was 5 years ago, this was the case. You need GPUs and memory because you are using full precision, and small devices which cannot supply such luxury of precision couldn't execute your networks. But with BNNs, with very small networks, even using the ARM processors, mobile ARM processors, very small mobile ARM processors, you can run networks, which will change the world actually. In that case, we'll have deep neural networks in $1 chips in our shoes, which will change the way of the world. So a BNN is defined, a binary neural network is defined by all binary numbers, guys. In the hidden outputs, weights, biases, activations, everywhere. That's why they are cheaper to store. Our memory requirements for binary network, deep neural networks, when we use binarized neural networks, BNNs, will be much, much lower. So comparing it to a single precision floating point representation, widely used in DNNs and GPUs. So you're representing them in a single bit. So from 32 bit single to 1 bit. You are getting 32 times efficiency in memory only. And in computation, since you are using bitwise operations, which are usually a single cycle in CPUs and GPUs, instead of floating point operations, which are usually tens of cycles, you are getting many efficiency in computation as well. So they are cheaper to compute, they are cheaper to store. That's why we have to learn how to use them. Okay, how? Well, I've taken the pseudocode from this website. I'm going to just visit the website, so let me visit it so you see what is it. So it's a very nice blog. As you might have realized, I'm visiting many blogs and papers, guys, because the deep learning society is fantastic in the sense that in the deep learning society, there are many guys, they are working in San Francisco and the Silicon Valley, they read complex papers and they take this as a mission that having a blog and explaining it in a simple way. And they become famous for it. And there's even they are rivals in this. They fight for it, who's trying to make the best simple explanation for networks. So just keep on these blogs, guys. I always read these blogs. That's a very nice blog. So paper explanation, binarized neural networks. We're going to see the paper as well. But it's a simple way to explain it. Because, you know, papers look very mathematically complex, but this guy explains it. And in this architecture, actually, this guy takes the this pseudocode from the original paper, which we are going to see in the slides. So this is the architecture or the pseudocode of it. Let me get to the slides. So what is the pseudocode for the inference, for only the forward operation? How do we do it? Actually, what we do it is, guys, imagine K is the number of layers. Sorry, L is the number of layers. So K is the layer index. For all layers, we first binarize the parameters, which means using a function for each weight value, it could be anything. We get the binary value. We apply the multiplication using the binary values with the binary activations. The activations are the inputs, which are the activations of the previous inputs. So like this, these are X's are AKs, and -1 and +1 are the WKBs, binarized weights. We obtain SK. We apply batch normalization if necessary. And if it is not the last layer, we binarize the activations and continue. So that's so simple. We have a binarization operation, which I didn't show you yet. I'm going to talk about how to binarize a value. We'll apply it in the network. Well, we've done a similar thing. You'll remember in our previously in MATLAB, we have on LXNet, we have put the precision from 32 bits to 8 bit, 4 bit, 2 bits. The precision goes down. So does this work? Well, if you do quantization-aware training using 2 bits, yes, it works. So I'm going to go into the details of this in the following slides.